Okay. All right, so I'm continuing with my idea, but I'm going to go ahead and do data augmentation rather than just one big model because I think it'll work better. So basically my idea is this. I'm going to try to build, whoops, let's do this. What we're going to do is we're going to train a system that takes in millions of different tabular data sets. And so there's some work that's done to create that data set already. So I'm going to use that and work from that. And then what I'm going to try to do is predict the distribution. So let's say this is a data set. Um, it's got, we'll say 5 features or whatever, how many features, maybe it's age, sex, maybe we're trying to predict their target credit score, whether they're going to default or not, age, sex, job, income, different features. So what we're going to do is we'll train a diffusion model to predict the distribution. I keep coming back to this and looking at this because it makes me think more clearly, I think, about what we're trying to do in machine learning and how important kind of the distribution, predicting the distribution is. So my goal is to basically what we'll do is we'll feed the network the first like row, and then we'll try to predict the rest of the rows. Seems crazy, and we'll do this using diffusion. So then we'll feed it 2 rows, predict the rest of the rows, feed it 3 rows, predict the rest, 4 rows, predict the rest, and so on. And by predict the rest, what we're actually going to be doing is we're going to be adding a bunch of noise to the rest of the data, and then predicting the noise. But basically the idea is to build a diffusion model that predicts the distribution of a data set. And we'll have to make sure we don't, overfit it on the specific data set. But I think it will work pretty well because basically the idea is what we're trying to do is build a model that is really good at figuring out data distribution. And so if we train it on tons of data sets, I'm hoping that the transfer learning works in such a way that there's a lot of common patterns that it can find in data distribution. And I really think there should be. And I just feel like this will really, like I was trying a different approach before, which like I think theoretically should have worked, but I just think that in practice, like the model is probably getting stuck in um, local minimums, and it's just focusing on the target too much um, rather than data distribution. I like this method for a few reasons. One, we're building a system that you give it some data and it creates more data. And I like that because I think it's an elegant way. So like somebody else could use the system by just generating, if they have a small data set, they could just generate more data and then they can train their own model. So it keeps the model, any sort of production model that they use, it'll keep small. It'll be simple to use. I'll make it simple to use so you can put your data set in there. So you don't have to like work with some huge model. This model is big, but the data that it'll generate will be reasonable. And then why else is it good? I'm hoping that like the transfer learning will work better in this type of setup than like a traditional target label setup. Oh, the other thing that's kind of nice is a lot of data sets don't really have target labels. You just have a data set, and so you might be able to get additional knowledge or transfer learning from those data sets in such a way that you don't need a data set that has a target, which I kind of like. Um, And the model will just purely focus on the distribution. I guess my main concern is that the model, like, so the, the, the only thing that's interesting about any of this is transfer learning. TR. If so if you don't have the transfer learning, in other words, if you're not getting information, if it's not helpful to get information from the rest of the world in your current situation, then it's just uninteresting. There's like use an MLP, use a simple model and train it. If that works better, it works better. Um, it would be disappointing if that, because right now for tabular data, no one has figured out how to use all of the information in the rest of the world. They're just looking at their current data. And to me, that's craziness. Like, there's got to be a way that you can use information in the rest of the world. I mean, a simple, like, it's so, to me, it seems, well, I guess to some degree this paper did, tab FBN, BFN, but they're actually not using information. They're using like pre-built heuristics, I think, to, and I don't know exactly what they're doing, to be honest. Something along those lines, though. But yeah, a model that can learn common patterns in data distribution, I think, is what's the important thing. I guess my main concern is that the model learn is basically overfits on every data set that I give it and isn't using the like generic enough distribution patterns. But man, I feel like there's so much data to train it on. I guess the big concern is that, I mean, it has to work. The thing has to improve. It has to augment data in such a way that it improves models. I think substantially. Um, I'm just trying to think if there's a way I can determine if it'll work before I try it. I guess there's like a few. My intuition thinks it will work. I think it will work. I'm trying to think what it'll look like at inference time. In other words, how I'll run it at inference time. And I think the way I would do it is the exact same way I train um, a single model. The concern at inference time is the risk of overfitting on that data set. I guess I could play with it a little bit, but I think, uh, yeah, I think, yeah, I think the way I would do it at inference time is the same way I train it. You have the person has a data set, and literally the inference will be takes the first row, predicts the rest of the data. Well, wait a second. Yeah, I could do that. I risk overfitting, so um, I risk overfitting, but there's information about how things grow, how your data distribution is growing that I think will be helpful that I want to get in there. So I've got to figure out the right balance there. I'm pretty sure this will work. So I'm going to try to think how else I could think about whether this will work or not. I mean, obviously I can test it, but the thing is, it's a little bit hard. It's hard to test the knowledge transfer without like doing a bunch of training. And the knowledge transfer is the only piece that's interesting. So I mean, I'll test it along the way to see like is it in the ballpark of working with only a little bit of knowledge transfer. I do feel like it's a good general approach though. I think it'll work. I can also add information about the data set that can give the model clues to how the distribution might go. Like, is it a medical data set? What are the columns in the medical data set? Is it a credit score data set? Like what, some meta information that I think will help it a lot. I think it'll work. I just think there's so many common data patterns in a system like this will kind of be very forced to learn those patterns and use them. All right, let's get ChatGPT to make the model. You gotta think about how much the see if that gets it. Let me go to the bathroom real quick. I thought I want to use. Um, yeah. Uh, I'm just trying to think about what to put in the actual model itself versus the training loop. So this, um, we're going to do the whole table every time. So the batch size is going to be huge. This is fine. We'll call this table. And then also in stable diffusion, you're supposed to have this idea of a step. So you add less, you're decreasing the amount of noise at every step. So okay, I'll get that. I'll get the actual the time step. I'll get the time step in a little later. Add noise. I had that, yeah. So use that. Do Okay. Let me see what ChatGPT comes up with when I tell it to. I'll just let it be broad. I don't know about passing it through. Maybe. Maybe. Okay, so it's averaging the feature embeddings, predicted noise. Yeah, yeah. I'm actually gonna work from this. It seems not crazy unreasonable. Not sure about those positional encodings, but let me just make sure this all makes sense. We got rows features. We loop through the rows. We do a little feature embedding. Yeah. So it is wanting us to embed the features. I'm not sure if we should. Stack all the embedded features to get a table. Yep. Row features demodel. Yep. Pass through feature-wise transformer. Yep. So this will go. Whoops. So this is pass through row-wise transformer. So that's actually not helping anything. We need to reshape things. So let's just not worry about this for now. Clean rows. Yeah, okay. We'll just do this. We will get this transfer over going, but for now we're just going to do okay. word transformer X, clean part, noisy part. Oh, no, no, I don't like that. Because, yeah, no, this is no good. We don't want to just use the clean part to predict the noise. Well, shoot. Yeah, no. Because it's a diffusion model, so we'll want to have the noise too. Shoot. Mm. This is going to have one too many dimensions. Okay. All right, so this will predict. This should predict the noise. So here's what we're going to do. Forget about this for now. We're just going to print the train loss. Prediction, actual noise. It's going to be the whole damn thing. We're going to forget about the positional encodings for a second. It's noise rows. Total number of rows minus noisy rows. What's this nonsense? What's going on with that loss? Whoa, okay. Let's see that again. Up, down, up, down, up, less up, down. It's an interesting loss. Up. That's funny. It's like going like up, big, down, down. It's like a bouncing ball. I don't know what to make of that. Bounce up. Oh, it's bouncing less. Watch this. This will be cool. Go down. Presumably it's got to be overfitting. Okay. Boing. Bouncy, bouncy, bouncy. Okay. The one thing that's interesting is, first of all, I'm kind of intrigued by this loss. I've never seen anything so uh, like with such a clear pattern. Just an interesting clear pattern. Um, so the evaluation. Um, for the evaluation, I think I need to add. Let's think about how to evaluate it. So it's the noise proportion. Let's see. I'm just going to directly pass it the noisy rows. For some reason, it's easier for me to think about as passing it how many clean rows. This would actually be noisy rows. So I'm going to say no, so total rows minus the clean rows will be how many? So when we're adding up the noise, we're going to pass it and then we'll just continue to actually, let's just do this. So we want to just we'll start with 2, and then we'll say every time we do it, and then we'll say it's close enough for government work. Now this is different. This is something's up here, something's off. It should be like jagged once we hit, oh no. Let's see when we hit 800, it should be like, I'm confused. Something's being weird here. Maybe the length is 1,000. It must be memorizing. Let's see. We're over 1,000 now. Yeah, okay. So that's wrong. What's going on here? Wait a second. Noisy rows. Num rows minus clean rows. I don't know what that was about. What's wrong? Clean rows equals 2. Should be going up. It is not going up. Ah. Okay, this needs to go down here. This is the per batch. Oh, yeah. Wait, clean rows equals 2. We're adding 1. This will just be one loop. What's going on here? What the hell? Can you not do that? And put 2 here. Pass it the whole damn table. Ah. Is this the problem? What's going on there? Where's the length of train? Ah, it's probably. There we go. Okay. Just make sure this is right. The actual noise will start out at big, like almost 800, then go down, right? Yeah. This loss go all the way down. We're predicting the noise. We're probably going to overfit. We go back up. We go back up. You know what? I'm gonna call epochs is weird. Come on. Well, mm, I'll reset the running loss. So basically, we gotta to get one loss. I'm gonna make it go through the one. It's actually not epochs, but we'll do one full. This is actually what we want to do. I don't know what to call it. It's not an epoch. Actually, this is better. I guess that's fine. So we start with 2 clean rows and we go to there's gonna be too many clean rows at the end of this. Eee. Oh my gosh. I wonder if it will have overfit like right away. Also, I'm a little bit curious. We're not using that much, not really using that much data. Hmm. You know, there's this question of how to evaluate the model. What's the evaluation score? And I'm trying to think if it's reasonable to give the model the training data and then have it predict the evaluation data and get those averages. I feel like it is reasonable to do that. Because then you'll see it start to overfit. Yeah, when the training loss increases. I think it's fair. I think it's fair. Mm, just want to speed it up a little bit, so I'm only going to do every 10. I know what the problem is. Add it to the rows. Ba-da-da-da-da. Should overfit. Oops, wait, let me just make sure. Yeah, current loader. Clean rows, that'll be the whole. Oh, no, that's right. Train table, UL table, predict noise, running loss. Interesting. Should be overfitting. It's curious to me that it's not memorizing. It should definitely be should memorize the training data. Not sure why it's not memorizing the training data. Seems weirdly closely correlated. I guess it's possible my model's too small. Let me see. Num heads, it's not small. Num layers, 8. And wait a second. Feature transformer. harder. Hmm? Nah, you crazy. What are you doing? What are you being crazy for? Oh, that's 1,000. Crap. Rows. There's 1,000 rows. Oh, but this rows is confusing. I'm just gonna call it batch. I know it's rows. Batch. Number of features. So batch. This would be, yeah. Number of features I think is 62. D is 8. Let's see if we can just. I'm just trying to make this transformer smaller. See if we can fit 1,000 rows into it. Well, our error is higher. Um, but I guess the noise is now harder to predict. Doing that attention across those 1,000 batches is tricky. So I think what we could do is just probably do like a subset, a random subset, if we can't fit it, or like if there's too many. Maybe like, yeah, not a random subset, but I hate to lose information. Error's going down. Um, so my diffusion model, it only has one step right now, so it's not going to work well. Wait, so you can add stable diffusion. I gotta, yeah, you can add noise on top of each other, right? Yeah, yeah. Let me figure this out. I know there's like a process for adding a specific like heuristic or process for adding noise so that you can add it on top of itself and it works. What math, it works. But I do need some help from ChatGPT to figure that out. I don't know why this is not overfitting. So I'm trying to think how I should do it. So yeah, we passed a time step with the noise, or basically, yeah, we can call it a time step. But how many? I don't like the word time step. It's weird in that context. Basically, we want to pass to the model how much noise we've added, and we'll increment it into. Yeah, that's it. So how much noise? Yeah, what level? How much noise? We just want to pass. They call it a time step in the diffusion thing, but I think it's easiest just to call it like how much noise have we added, and we'll do noise levels of like 1 through 10. 1 would be the least amount of noise, and 10 would be the most, or something like that, or maybe vice versa. But we'll pass to the model they call it time step. I think I'm going to call it amount of noise. Well, 1 second. I got to do a refresher on diffusion. Uh, diffusion. Um, I gotta find some code. I've written some code about this diffusion before. I gotta find it. And this is the comprod. What? Okay. Mhm. Okay. It's kind of easier just to add some amount of noise and then predict it rather than this diffusion. But yeah, I got to do the diffusion. Got to do the diffusion. I think this is. I think I did it. Yeah. I think I remember following some tutorial. Uh, um, this guy is so good at explaining stuff. It's incredible. Okay, I thought he had a GitHub tutorial on this. Maybe not. Must use a different one. Um, ugh, this is terrible. Actually, maybe this is the one I was using. This looks right. So, pipeline. Okay. must be training this somewhere though, right? Where am I training this? Oh, no, no. Oh, okay. Okay, so it looks like when I'm training the diffusion, the way I do it is I get a random time step between 0 and 100. And it looks like I need to predefine these time steps because this linear beta schedule, betas, okay, well, okay, 4 diffusion samples. So I pass it the anchor image, the time, and I'm also using a mask, which confuses, which makes things complicated. But so noise is random, like so we have random noise, size of the image, square root. Okay. Crap, I'm adding this mask. It's making things confusing. Mean plus variance. So this is what's adding the noise. So I need to update my thing to do this. Noise prediction. And then we just simply predict the noise. Takes an image and a time step as input and returns a noisy version of it. Okay, yeah. But we do need, because this is using these, right? Yeah, we need the square root alphas come. We need this. All right, here we go. I'll put this in here. I might need to get some lunch first, though. Go for my run. It's really not overfitting. It's weird. All right, I'm gonna take a break. I'll be back.